I'd like to welcome everyone to today's Construction R&D Showcase. I'm Mike Matheson, Managing Director of Cognit.ca, and will be moderating today's session. This series is jointly presented by Cognit.ca and the Canadian Construction Association. The R&D showcases are part of a broader initiative Cognit.ca and the CCA have undertaken to help the construction industry more fully leverage Canada's $14 billion academic research enterprise. Another major element of this is the Construction R&D portal, which can be found on the CCA website. Using the R&D portal, you can see recent construction industry relevant research and search for researchers, facilities, and IP that can help you address your company's next innovation challenge, and would encourage you to check it out when you have a few minutes. Our format today will be a 30-ish minute presentation followed by a 15-minute Q&A. If you have any questions for our presenter, please click the Q&A button at the bottom of the Zoom window and enter them in the box. I'll read them out during the question and answer portion of the program. For today's R&D Showcase, I'm delighted to welcome Dr. Amin Hammad. Professor Hammad is a full professor at the Concordia Institute for Information Systems and Engineering. He will be presenting on using AI to improve safety and productivity of construction projects. With that, I'll turn it over to Dr. Hammad.
Good afternoon, and thank you for the introduction. So as mentioned, I will be talking about using AI to improve safety and productivity of construction projects. Again, my name is Amin Hammad. I'm professor at Concordia Institute for Information Systems Engineering. Okay, let's see this one. So the agenda of my talk, I'll start with a general introduction. I will define in a brief way what is AI and smart construction. Then I will give some examples about object detection and tracking on construction sites, followed by some safety and productivity applications. Then I will talk briefly about construction robotics, and I will end up with future research directions and some potential resources if you have the interest to have more details. So let's start with a quick introduction about the major problems in the construction industry which are related to productivity and safety. So as you can see in these figures, here we have the construction industry curve versus manufacturing. And we can see over the years, the manufacturing industry had improved its productivity up to about 56%, while the construction industry in Canada was almost at the same level or even declining a little bit. And this pattern can be seen also in other countries. In this figure, we have similar pattern for the OECD countries. In addition, we can notice that we have low percentage of companies investing in innovation compared with manufacturing. In the province of Quebec, the percentage of companies investing in technology is about 4%, while the ratio is about 50% for manufacturing. Regarding safety, here we have some numbers from the US. So in 2017, we had about 47% of the total number of fatalities related to the construction industry, which is much higher than most other industries. And we see in this figure two types of accidents related to struck by vehicle and struck by object or equipment. And we can see, although there is some reduction in the numbers, still the rates are very high. So with this respect, maybe we have to explore the potential of AI and smart construction to remedy these issues. So let's start with defining what is artificial intelligence. So AI is the system's ability to correctly interpret external data, learn from such data, and use those learnings to achieve specific goals and tasks through flexible adaptation. So we will see in more detail about these different aspects, specifically the learning aspect. And some areas of AI are expert systems, which were very popular in the 70s. More recently, we have more applications of machine learning. We'll talk about neural networks and deep learning. And we have some applications in speech recognition and computer vision. So speech recognition, some of us are familiar with Siri and Alexa. We can ask some simple questions to Siri or Alexa, and even in that case, we don't get always the perfect answer. So we can see that we still have a long way for the practical application of AI in our daily lives. Related to computer vision, I will be showing you some examples related to object detection and tracking and activity recognition for some activities on the construction site. Another very active area is robotics. So we know about self-driving cars, where we can depend on the sensors and so on to collect data that can be used for path planning. AI is a disruptive technology, and the acceleration in AI research is happening because of multiple factors. We have the advancement in machine learning. As I mentioned, we have the artificial neural networks, and we have also the more advanced deep learning that can exploit a huge amount of images and other types of data to improve the performance of the machine learning. We have the increasing hardware computing power, whether it is CPU, GPU, or RAM. We have the widespread of sensors and IoT, Internet of Things, that will result in collecting big data, and this data can further improve the machine learning. And we have also better networking. So we have pervasive computing, cloud computing, edge computing, different types of levels that can be done using the networking capabilities. Now, related to smart construction, here we have a figure that tries to position smart construction with other related concepts. We have smart manufacturing, smart buildings, smart structures, smart materials, and so on. So even we have smart helmets, for example, that will help in improving safety on construction sites. And a smart system can incorporate functions for sensing, actuation, and control in order to describe and analyze a situation and make decisions based on the available data in a predictive or adaptive manner. So as you will see, we will start with sensing, and this sensing can be used to make some decisions through the actuation and control of the different devices. Here is my definition of smart construction. So smart construction aims to use automation to improve productivity, safety, and quality. So with respect to productivity, we can improve progress monitoring. We can achieve better level of the concepts of lean construction. We can use the sensors that will give us data about the health of the equipment, and we can use that for resource allocation. With respect to safety, we can avoid collisions. We can, as I mentioned earlier, use the information for path planning and so on. Regarding quality, we can also reduce the rework, and that can achieve better levels of quality. We can do all of that because we can benefit from multiple types of sensors for data capturing and telematics. We can use the data for real-time data analytics and distributed decision making. And here it's important to mention that it's not necessary to achieve the fully automated side, because we would like to keep the human in the loop in the decision making, especially in construction sites. However, we have a problem related to the cost of automation. So automation is costly, as we see here in this figure, coming from a study from McKinsey. We have the hourly wage of different jobs on the x-axis versus the automation potential using current technologies. So these are for different jobs, as I said, but I extracted those related to construction. As you can see, most of these jobs are not highly paid. So that could be a challenge to justify the cost of automation or using robots on construction sites. Let's move to object detection and tracking on construction sites. So we start with, as I said earlier, we start with sensors. So the sensor data will be collected for resource tracking. By resources, we mean materials, workers, and equipment. We can do also the site surveying and modeling that could result in near real-time for the building information models. We can also benefit from other types of sensors like weather stations or sensors related to the health of the equipment. We can combine all this information to answer multiple questions: what, where, when, doing what, or under which conditions. So related to what, we can detect the different types of objects like excavators, trucks, and so on. And even in some cases, we can identify them in a unique way. For example, we can distinguish an excavator 1 from excavator 2 and relate that to their activities. For the positioning, we can detect the position, and also the pose. For example, if we have articulated equipment or workers, we can see the specific pose of these objects. Of course, we can also relate that to the date and time. We can go further and detect the activities. For example, an excavator is in loading or swinging position, and then we can relate that to other site conditions like the weather conditions. This figure shows different tracking technologies. We are familiar with the global positioning system that is widely used. We have other types of real-time location systems, or what we call here RTLS. For example, we have RFID, radio frequency identification. We have ultra-wideband and other technologies based on radio. We have the computer vision that's becoming more and more applied in construction sites. We have onboard instrumentation, and also we can combine different types of sensors to achieve better results. So we call that data fusion. We can fuse the data from different sensors as needed. The figure here showed the relationship between the coverage versus the accuracy of different types of tracking systems. So the ideal situation is here. We have the highest level of coverage and the highest level of accuracy, which is not easy to achieve using current technologies, but we can choose the suitable technology based on the requirements. For example, here in the middle, we have ultra-wideband that has a good balance between coverage and accuracy. These are some early examples of using RFID technology for material tracking. So these are a kind of replacement of barcodes or other types of labels that will allow us to identify the objects from a distance based on radio signals. And this has been applied in different types of applications. We did a recent study about a couple of years ago with Hydro-Quebec, which is the major power company in Quebec. So they had a large construction site. We installed sensors for location tracking. We installed a specific type of real-time location system based on Bluetooth technology. So as you can see here, we have 4 poles that have been installed. And then on each pole, we have a sensor, which is this rectangular shape. And then we have also cameras. As you will see later on, we use the cameras to collect videos to be used for the computer vision. Also, we have on each pole a wireless antenna to transmit the data from the sensors and the camera to the site office where we can do the analysis. One of the issues when we install sensors on construction sites is that we need a lot of cables, and that could be also an issue in practice. So we try to eliminate as much cables as possible by using this wireless communication. This is what we can get from these cameras and real-time location system. We have this three videos coming from 3 cameras on pole 1, pole 2, and pole 3. And then we have also the data from the real-time location system. We have these dots that are showing the location of workers and equipment, and that will help us to identify proximities. For example, we can define a threshold. If the distance is less than 2 meters, we can generate an alert, and this alert could be transmitted to the worker who is involved in this situation through vibration signals or other types of signals. So we did that in a small test. And to do that, we have, in addition to the sensors, we need to install tags on the different objects. So we have some tags attached to the hard hat of the workers, and also tags attached to different types of equipment. So as you can see here, we have multiple tags to provide some redundancy. If a tag is not functional, we have other tags, and also that will improve the quality of the collected data. In addition to the real-time alerts, we can also generate a report at the end of the day that will tell us about all types of proximities, could be near misses or could be real accidents. So here, for example, we have a proximity between a crane that has a specific ID and the worker that has another specific ID at a specific date and time, and also we have the distance between the objects. We can also, as I mentioned earlier, track workers using computer vision. So here we have multiple workers that are tracked. As you can see, we have these frames that are showing the detection of a specific worker, and they are shown with different colors. So somehow we are identifying different workers. But look at this one. It is red here. When the worker is obstructed by the machine, the color is changing to green. So the machine learning here is not able to 100% identify that this is the same worker. So this is a problem related to computer vision. There are some solutions for that, where we can add a marker on the hard hat, let's say, and that will allow us to uniquely identify each and every work. In addition to detecting the equipment as a whole, we can also detect parts of the equipment. So here we can detect the boom and other parts of the excavator, and that will allow us to identify the skeleton or the pose of the excavator. That could be used for identifying the activity of the equipment. This table shows a comparison between the computer vision and real-time location systems with respect to different factors. For example, we have issues in construction sites like occlusion, as I showed you in the previous slide. Computer vision cannot deal with occlusion. We have also sensitivity to light and weather conditions. For the RTLS, we have line of sight issues also, but not as severe as the problems of occlusions in computer vision. So we can have some tolerance with respect to not having line of sight. We have also sensitivity to radio signals. If we have radio noise on the side, that may affect the performance of the system. The installation could be also is an issue. As I mentioned earlier, we need a lot of cables. We need to install the sensors and cameras at certain height. We need also to consider the privacy issues. In case of RTLS, the workers may not like to be identified. And also, as I said, we need to install tags on each and every worker. So that will need some kind of negotiation with the worker unions and so on. The cost could be a little bit higher for RTLS, where on the other side, for the computer vision, we just need to install cameras. The computer vision will require the training for the machine learning, while the RTLS does not require that. The processing time for computer vision is usually longer, so that may cause a problem for real-time applications. Of course, the hardware is improving, and these issues could be overcome in the future. The last factor is the ability to identify unique objects. As I mentioned, it's possible with computer vision, but it's not straightforward. While in the case of RTLS, every tag has a unique ID. Now let's look at some applications related to safety and productivity. Here we have an example for hard hat and safety vest detection. So as you can see here, when the camera is close to the worker, the results are very good, almost 100%. When we are away, like here, the vest detection may not be as good as we want. And of course, in real situations, the camera will never be as close as we see in this video. So I'm going to show you other examples where the camera is further away. So this is the same site I mentioned in the previous slide related to Hydro-Quebec. So here we have the example of personal protection equipment non-compliance. We have the driver of the truck who left the truck without the hard hat and the safety vest, and the computer vision was able to detect that. And on the other, in the other image here, we have the proximity near miss. So we have a worker who came close to the excavator. We have the work area of the excavator, and we have kind of near miss situation. So we can detect these proximities, and again, we can generate reports that can be used by the safety manager. In order to define the workspaces of the equipment, we studied different cases based on the specific situation of the equipment. So in this case, we have the excavator that could be in swinging state, loading or dumping state, and so on. And that will affect the shape and size of the workspace. That's very important because we would like to keep the workspace as small as possible. The reason is that if we have a larger workspace, let's say if we use a cylindrical shape or a circle surrounding the equipment, that is easy to do, but it will generate a lot of false alerts. So that will affect the efficiency of the system because the workers will become less sensitive to these alerts. Another way to look at the workspace is to predict what will happen in the near future. So we call that look ahead equipment workspace. You see this interesting shape of the workspace of the excavator. And this will be calculated based on the movement patterns of different parts. So we have here the movement during loading, during dumping, and so on. And we can use this information that is based on the prediction in the near future to generate the shape of the workspace. That can be used to calculate the risk map. So here we have these different cells with different colors, and the color is representing the level of the risk. So red means higher risk, green means lower risk. And this will be calculated based on different factors. We have the shortest distance to the equipment. We have the shortest time, or time to the shortest distance, which has to do with the time of movement. And we have also the blind spots. So we can combine these different factors in an equation, and that will give us the risk index for each of these cells. And that will be generated in 3 dimensions. So here we have the shape of the workspace and the resulting risk map. Again, the red color means higher risk. Let's look at some examples related to productivity. In this case, in the first example, we have a loader loading multiple trucks, and these trucks are going from the loading zone to the dumping zone. So based on the different zone that we can define, and based on the location of the equipment, we can identify some rules to tell us whether the truck is dumping or the excavator is dumping. So in this case, we are simply defining the rules based on location, and we can create different rules to identify different activities. We applied that in a lab experiment. So we attached tags on the equipment. These are remotely controlled equipment. And we try to simulate what's happening on the construction site. And we can identify for different time steps. Here we have the time on the horizontal axis. What are the different states of the truck and the excavator? And that could be synchronized with the movement of the equipment. We can do something similar using computer vision. So in this study here, we try to apply the activity recognition using computer vision. And in this case, we had to use different types of deep learning methods. So I'm not going to discuss the details. We have different types of machine learning and deep learning tools that can be applied for the detection, tracking, and activity recognition for excavators or other types of equipment. Okay, and we can even identify the grouping of different equipment. So for example, here we have 2 excavators. Each of them is working with a set of trucks. So we can identify within each group what are the activities, and later on we can use that for productivity analysis. So we start with the identification or the detection, then we move to the tracking, and then to the specific activities for each excavator. This is a video showing how things will work in practice. So here we have the different activities of the excavator, and we have the cumulative time. These small bars are showing how much time has we spent for digging, swinging, or loading. And at the end of the period, we can calculate the average cycle time, and that can be used for calculating the productivity. As I mentioned earlier, we can do that for more than one group. So in this case, we have 2 groups, and we can do exactly the same thing for excavator 1 versus excavator 2. Notice here the complexity of the situation where we have partial occlusion. So the further excavator is partially obstructed by the other excavator. Still, the computer vision is able to detect each excavator. We can also try to identify the idling reasons. So going further than identifying the activities and the cycle time and the productivity, if we notice lower productivity, what could be the potential reasons? So in this study, we try to analyze the idling reasons. We have 4 or 5 cases. We have the excavator waiting for a truck. So the truck is not coming, so we can easily identify this situation. We have the case where the truck is maneuvering to be loaded by the excavator. That will add some delays. We have another case of congested site. We have more than 2 trucks near the excavator. That will add more delays. We have also some cases where it's not easy to identify the reason based on the data that we collected from the video. there are some cases where we cannot see the specific reason. For example, it could be a malfunction of the equipment. So in that case, as I mentioned earlier, we need extra data from health monitoring sensors installed on the equipment maybe, and that can explain the reason for the idling. Another study we did based on computer vision is to create the digital twin of the construction project. So here by digital twin, we are referring to detailed 4D simulation models that will reconstruct the beam, the BIM or the building information model at different points of time. So here we have some activities related to building foundations. We have the formwork, we have adding the steel rebars, pouring concrete, and so on. So for each of these steps, we can extract the information using computer vision and use that to recreate the 4D simulation. The 4D simulation in this case is combination of the 3D model and the activities that have been identified using the computer vision. So that's what we are going to call the as-built 4D simulation. Now for the activities, again, we can do something similar to what we did for the excavators and trucks. We can identify the different activities of the workers, standing, hammering, transporting, drilling, and so on. And again, linking that with the previous project, we can track the work, we can identify and track the workers, and then identify their activities and combine that with the information related to the product or the work that has been achieved, and that can be used for productivity calculations. The last part is related to construction robotics. So I'm going to go through this part quickly. I know there was another talk related to this issue. So I'll just show you quick examples. Here I have some benefits and challenges of applying robotics in construction. So on the benefit side, we have the ability to cover the shortage of skilled labor. We can improve efficiency, quality, and safety, and we can reduce the cost. Eventually, we can reduce the cost, although the initial cost could be a little bit high. The challenges, we have the complexity of site conditions compared with manufacturing environments in the factory. Of course, the construction site is much more complex. We have also the cost, as I mentioned, the initial and maintenance cost of the robots. We have the problem of the low level of standardization. So to be able to use robots, we need to have accurate information about what's happening on the site. Of course, we have some initiatives to use BIM in construction, which is becoming more and more applied in practice, but still is not enough to fully apply robotics in construction sites. And also we have the limited coordination between stakeholders. Here we have a quick overview of the different types of robots. We have autonomous robots versus teleoperation versus exoskeletons. So we have different things that could be considered as different levels of automation in the construction process. We can also have two major groups of fixed versus mobile robots. An initial usage of sensors in construction equipment is what we call automated machine guidance and control. So here we don't have specifically AI, we just have the highly accurate GPS receivers that could help in controlling the level of the blade of a grader, for example. Okay, so if we have the design data and we have the real-time data from the GPS, then we can move the blade up and down, and that can achieve very good level of automation. This slide shows different types of single task robots. So we have here welding robots, we have bricklaying robots, we have rebar tying robots here. We can have also deconstruction robots. I don't have it in this slide. We have very advanced robot from Japan for drywall and panel installation. Of course, this will be much more expensive robots. The same thing for the other robot that looks like a dog here that can move on a construction site and collect data using different types of sensors, could be cameras, could be laser scanners. And we can use, similar to this one, we can use a more basic type of robots to go on the construction site after working hours and collect data about the work that has been achieved that could be used for progress monitoring and quality control. This is an interesting example from Japan, from a company called Shimizu, which is one of the major construction companies in Japan, and they call it Shimizu Smart Site. So here we have a fleet of different types of robots that can collaborate and work together. We have a robotic crane that will work in all weather cover or under all weather cover. We have a robot welder. We have a small robot that can help in multi-function applications. And we have a carrier robot that can move the materials from one place to another. So the interesting concept here is that we don't have only a single robot doing a single task. We have multiple robots doing different things, and they can work together. Finally, I have a slide to quickly review the future research directions. Of course, we need a lot of time to discuss about that, but I will explain in a brief way. We need better sensing and control. We need easy to install and rugged sensors. So on construction site, the sensors may have multiple issues because of the cold weather, because of the different conditions on the construction site. As I mentioned, we can fuse the data from different sensors to achieve better performance. Also, we need to think about the automated site as a kind of cyber physical system where we have to think about different issues, including security. So this is one of the topics to be discussed in the future. We need better decision making. So here we can benefit from distributed computing and multi-agent systems and the big data analytics concepts. We need better interaction. So here we have the human-computer interaction. We have a huge amount of data that will be collected and need to be visualized. And for that, we can use perhaps augmented reality. And we need also human-robot collaboration. As I mentioned at the beginning, the human has to stay in the loop. So we need to have the workers working with the robots in a safe environment. Other issues could be related to safety regulations. So in order to introduce these systems in actual projects and depend on them, we have to see how to link that with safety regulations. So in fact, in the project that we did with Hydro-Quebec, there was an argument that perhaps we should not have this technology because it will create kind of dependency on the technology. We have the security and privacy issues. Privacy is a big theme also. So as I mentioned, when we install the tags on the hard hat of the workers, that will allow us to identify uniquely each worker. Also, the computer vision will allow us to see the faces of workers. So when we discussed with the general contractor, and in fact, we went through the legal team of Hydro-Quebec to see how we can resolve these issues. And the main argument that we use is that we are applying this to improve safety. So in this case, maybe the privacy issues could be less severe. At the end, we have the idea of process re-engineering. So at the time being, we are doing things most of the time depending on the workers and their ability to achieve different tasks. But now we are moving to another level of automation, may involve different types of robots and also different types of data collection and analysis. So we need to think about how to re-engineer our processes. At the end, I would like to share with you some of the journals and conferences where you may find some interesting documents or papers. So the main two journals that we use to publish our research are Journal of Automation in Construction, that's published by Elsevier, and the Journal of Computing in Civil Engineering, published by the American Society of Civil Engineering. A major conference is called International Symposium on Automation and Robotics in Construction. This is sponsored by an association called the same name, actually, International Association for Automation and Robotics in Construction. And the next conference will be in Dubai the first week of November. We have, my students have about 6 papers in this conference. And it will be online. So if you are interested, you can attend online. Also, I I'm the co-director of the Center for Innovation in Construction and Infrastructure Engineering and Management at Concordia University. It's a leading research center in Canada focusing on automation construction. We have about 20 professors from 5 academic units, not only civil engineering, we have also people from systems engineering like myself and other colleagues from mechanical and electrical engineering. And we have major industrial partners, including Canam, Hydro-Quebec, Hatch, SNC-Lavalin, and so on. And if you are interested, I'll be glad to discuss with you. There's no fee to become member, and the benefits would be to have access to workshops and some talks like the talk that I'm giving today. And also we can have some discussion about potential research collaboration. Thank you.
Thanks, Professor Hammad. So we'll now move to the Q&A session. And if you have a question for your presenter, I'll just remind you to please use the Q&A box at the bottom of the Zoom window. I'll try to get through as many of your questions as possible in the time remaining. I want to pick up first off on that last theme that you touched on, which is areas of possible research collaboration between businesses and academic researchers. You provided a long list of areas where you think future directions of research are going and areas of inquiry that are active. Could you talk a little bit about whether there's a few areas or maybe nearer term projects that you think would be particularly well suited to a university business research collaboration?
Mm-hmm. Yeah, actually, maybe the best example I can refer to is, again, to go to the project that we did with Hydro-Quebec, which is recent, about 2 years ago, and we are still collaborating with them. So this could be a good example about how to start. So in this case, as I mentioned, the starting point was to select a suitable project, not too big, not too large. This is relatively a larger project, but they have much bigger projects for building dams and so on. We also had to struggle with the way to install our instruments. So this is by itself a task to be considered without disturbing the workers, without interfering with their daily job. Another aspect was how to convince because of course the Hydro-Quebec was the owner of the project, how to convince the general contractor to be also a partner on this project. I mentioned a little bit about the privacy issue and how to create a useful discussion, for example, that we are trying not to spy on the workers. We just want to improve their working conditions and focusing on safety. So to answer your question, I think the first step is to identify a niche for a specific company, whether they are interested in safety or productivity or quality or other aspects, and then to define a well-defined scope, not too big, and also to have realistic expectations. So like even when we started with Hydro-Quebec, they were thinking that we have something like a product that we can just apply. We can push the button and get all the results without any issues. In fact, we developed the tools, we had to test them, and what we do is based on the work of our students. So we are not in a position to have a fully supported product that has all the bugs fixed and all the problems solved. So the idea of having collaborative research is to give the company an entry point to test what's happening in these types of projects or this type of technologies. In fact, there are some companies who are selling some solutions that are similar to what I discussed today. But when you talk to these companies, they will be charging maybe 5 to 10 times what we ask for collaborative research. So, and also we can customize our solutions to fit with the requirement of the company. And then if there is a desire to go further, there are also ways to further develop the solutions to become practical and applicable in real life. So I have to stress this point. We do research, we don't develop products, but this basic research can be translated into real world products. So this could be also discussed.
One thing that you noted in one of your subsequent slides was that a challenge to computer vision was the need to train the models to recognize activities and near misses and things like that. To what extent are pre-trained models usable? I know in some domains of ML and AI, pre-trained models are state of the art. Is that the same in these kinds of applications? Or
yeah, that's a very good question. So actually, for example, in this research, we had to train our network to detect excavators. So as you mentioned, these models come with some pre-training data set. So they are already trained to detect different types of objects. Could be for cats, dogs, tables, plenty of different objects. And they have nothing to do with the construction equipment. However, this basic ability can be used or reused. Of course, we have to bring our own data set and train for the specific object that we are trying to identify, but we call that transferred learning. So transferred learning means that the pre-training for this model allow them to detect simple features like the edges that we see here. Although this is not our main interest here, but the pre-trained models can be reused to improve the training and make it more specialized. And there are plenty of methods and new techniques to make that happen in a more practical way. So as you mentioned, the training requires us to collect a lot of data, which is by itself a hassle. Then after we collect this data, we have to annotate each frame. So for example, we want to detect the excavator, we have to use the video that we used for training, and on each frame, we have to draw a box to say that this is the excavator. So this is called supervised learning, and then it will add to the time and effort that is needed for the training. Okay, so there are now new methods that will try to accelerate that process to reduce the time that is needed for the training, as well as reducing the need for large data sets. So all of these are still research topics.
And when you think about the retraining or the transferred learning, once you've trained a model for a particular type of job, does it transfer across job sites, or is it still something where new camera setup requires a new training?
That's also an excellent question. So as I showed you in different slides, let's say the project of Hydro-Quebec, we installed the cameras on that site, and we used the data from the same site for the training. Of course, we had also other data from YouTube, from other sources that could be useful also for the training. Now, if you use the data from the same site, of course, the quality of the training will be much better. For example, we can, when we do the detection, we can use the training coming from similar conditions, from the same weather conditions, from the same height of the camera, from the same, even the type of the equipment. We have different equipment that look similar, but they have different characteristics. So the more similarity we have between the training data set and the actual data for the detection, the better the results. So to answer your question, we can benefit from both. If we go to another construction site, the pre-trained model that we have will function, will work. But then we can continue collecting the data from the same site, and that could be used to further improve the training.
That's fantastic. I really appreciate your time. And that really does bring us to time for this session. So first of all, I'd like to thank Dr. Hammad for his presentation. I know I found it extremely interesting and learned a lot, and I'm sure others did too. I'd also like to thank Kenny, Nicole, Mary, and the rest of the team at the CCA who have been so instrumental in pulling this session and really the whole series together. Without them, this would not simply not have been possible. Lastly, I'd like to thank all of you for coming out today. I know your time is scarce and precious, and really appreciate you fitting this into your busy schedule. On that note, we're really focused on ensuring these sessions are as valuable for you as humanly possible. And to that end, we've put together a short evaluation form that we'd really appreciate if you could fill out. I've pasted a link to it in the chat window. It should only take 1, maybe 2 minutes to fill out at the most. And if you haven't closed your browser already, it likely will have opened in the Zoom tab. Your honest feedback is really critical to us as we try to make this series as big a success as possible and as valuable to you as we can. Thanks again, and I really hope everyone has an excellent rest of the week.